Hi everyone, this is question 3 of the NZQA Scholarship Chemistry exam for 2022. Let's get straight into part A. A saturated solution of calcium hydroxide was prepared by mixing an excess of solid calcium hydroxide with a small volume of water at 25 degrees Celsius. The solution was filtered to remove remaining undissolved solid, and the filtrate was then used to fill a 50 ml burette. 20 ml of 0.0308 ml per liter ethanoic acid solution was prepared into a conical flask and titrated with the calcium hydroxide solution using an appropriate pH indicator. Calculate the volume of calcium hydroxide solution that was required to reach the equivalence point in the titration, and they give you the Ks value. So looking at this, we're thinking what volume of calcium hydroxide solution is required to reach the equivalence point, which means what volume of calcium hydroxide is required to fully neutralize the ethanoic acid solution. We can figure out the number of moles of ethanoic acid solution quite easily given by the concentration and the volume, and so we can figure out the number of moles of hydroxide ions which were used to neutralize that, and that is given from the calcium hydroxide solution. So basically, we can figure out the number of moles of calcium hydroxide. We can figure out the volume of calcium. We can figure out the number of moles of calcium hydroxide, and we need to figure out the volume, which means all we need is a concentration of hydroxide ions in the calcium hydroxide solution, and that is simply just the case of figuring out the figuring out numbers from the Ks value. So as we know, calcium enters into equilibrium with hydroxide ions to form calcium hydroxide. And the Ks for this reaction is 6.40 times 10 to the negative 6. That means we can write out the Ks again. So it's the concentration of calcium times the concentration of hydroxide squared, and that's equal to this. And so looking at this, it's quite hard to figure out what to do next, because we could try to figure out the concentration of hydroxide ions because that's what we need eventually. But we can't figure out what the concentration of calcium ions is from the information they give us. However, it is quite a well-known principle. Hopefully you already know this by now. But because the calcium and the hydroxide ions enter into equilibrium together in a 2-to-1 ratio, the calcium concentration is actually just half that of the hydroxide concentration. So we have, this is actually equal to half OH minus, because the calcium concentration is half that of the hydroxide concentration, times the hydroxide ion concentration squared again, which is equal to half OH minus cubed. So what does that give us? That means that the concentration of hydroxide ions is equal to 2 times the Ks cube rooted. So if we put this into our calculator, so we would have cube root times 2, or cube root of 2 times 6.4 times 10 to the negative 6. And that gives us 0.0233, oh, that is a terrible looking 2339 moles per liter. So that's the concentration of hydroxide ions. And from there, it is pretty straightforward now. We know that the number of moles of ethanoic acid, which was titrated, CV, and then it's the concentration of the ethanoic acid times its volume in liters, So we have to divide by 1,000. So 0.0308 times 0.02 is 6.16 times 10 to the negative 4 moles. And that means that is the same as the concentration of hydroxide ions, because the hydroxide ions and the ethanoic acid solution would react in a 1-to-1 ratio. And so they would be equivalent at equivalence point. So then we have the concentration of hydroxide, we have the number of moles of hydroxide. Volume of hydroxide is simply then number of moles of hydroxide divided by the concentration of hydroxide. So that's number of moles is 6.16 times 10 to the negative 4 divided by our concentration, which was 0.02339, and we get 0.02339, 0.02633 liters. And you can convert this to milliliters if you want, so that would be 26.33 milliliters. moving on to part 2 of question 3a. Determine the pH of the solution in the conical flask at the start of the titration at the equivalence point and after 35 mils of calcium hydroxide solution has been added. Include a brief outline of any assumptions made when calculating either the initial pH or equivalence pH. And if you're unable to solve the volume in part I, use 25 mils. But that's fine because we have the volume of part I here, 26.33 mils. And so, let's start with the first part of the question, which was what is the pH of the solution at the start of the titration? So at the start of the titration, you only need to consider the ethanoic acid in the solution. So ethanoic acid plus H2O goes in equilibrium with CH3COO minus plus H3O plus. And of course, you know the Ka is given by CH3COO minus H3O plus. This formula should be very familiar to you by now, hopefully. And that is equal to 10 to the negative 4.76. That should also be another formula very familiar to you. And, okay, because CH3COO minus and H3O plus are formed in 1-to-1 ratios, you can say that the concentrations of ethanoate and hydronium is the same. So then you just get H3O plus squared divided by CH3COOH equals 10 to the negative 4.76. So then you have H3O plus, concentration of H3O plus is equal to, so whenever you're making pH calculations, your final goal is always to figure out the concentration of hydronium ions. And so we get concentration of ethanoic acid solution at the beginning was 0.0308. So then we have 0.0308 times 10 to the negative 4.76, all square rooted. And that is equal to 0.0308 times 10 to the negative 4.76. That is equal to 7.316 times 10 to the negative 4 moles per liter. And so pH is just the negative log of that. I won't write it out. It's a very simple formula. So 3.14. So that's the pH at the very beginning, 3.14. But along the way, we have actually made an assumption here. So obviously, they tell us to write a brief outline of any assumptions made. So we have an assumption here, which is here. And it's that the concentration of the ethanoic acid solution, the concentration of ethanoic acid in the solution is 0.0308. In reality, it's not always 0.0308 because the ethanoic acid solution would have dissociated to form other things. And so, although we might have initially measured it to be 0.0308, it would have dissociated, and so it would be slightly less than 0.308. In most cases, the amount by which CH3COOH dissociates is very, very small, and so you actually wouldn't need to worry about it at all. But it is good for you to point that assumption out in this question, so we have done that. Okay, second part of the question is at equivalence point. Okay, at equivalence point, we know that the CH3COOH plus the hydroxide ions that were added from the calcium hydroxide goes completely into CH3CO minus plus water. And in this case, because it's equivalence point, let's just separate this. Because it's equivalence point, all of this has been neutralized. So 0 moles per liter. And so the only sort of component or conjugate part of ethanoic acid solution present in the solution is the ethanoate. And why is that important? Because when we consider pHs at equivalence points, we always have to consider the species involved. So usually we would have CH3COOH plus H2O gives us CH3COO minus plus H3O plus. But because we have no CH3COOH in the solution, because it's been fully neutralized, this approach no longer works. And so the approach that I like to do is instead you consider CH3COO minus as the main contributor here, because we actually have this in our solution from the neutralization process. And so this reacts with water to form CH3COOH again and hydroxide ions. So the ethanoic ion is essentially acting as a base here. So we can write out the Kb expression. So if you're not familiar with Kb, it's like Ka, but instead of for acids, it's for bases. So Kb in this case is the ethanoic acid. Hydroxide ions, so same idea, CH3COO minus. And that is equal to 10 to the negative 9.24. And 9.24 is simply because the pKa plus pKb, this is just a formula that you should know, is equal to 14. So pKb is equal to 14 minus whatever pKa was, 4.76, which is 9.24. Okay, great. And we also know that Kb, or in the case of Kb here, the ethanoic acid solution, the ethanoic acid concentration is the same as the hydroxide ion concentration. So it's the same logic. So it's the hydroxide ion concentration squared divided by that, and that is equal to 10 to the negative 9.24. So now we just have to figure out what is the concentration of the ethanoate ions. We know that the number of moles of ethanoate ions was given by this up here, because that was the number of ethanoic acid molecules that was reacted. So number of moles of ethanoate is equal to 6.16 times 10 to the negative 4. The volume of, let's just say the solution. Well, we know that initially we had 20 mils, but then we also added, at this point we've added 26.33 mils, because we've reached equivalent point. So the total volume here is the initial 20 mils plus the equivalence, or the mils required to reach equivalence point. So actually the total volume is 46.33 mils. And so the concentration of ethanoate is 6.16 times 10 to the negative 4 divided by 0.04633, because again, convert mils to liters, divided by 1,000. So what's it? 6.16. Sorry, let me just fix that. 6.16 times 10 to the negative 4 divided by 0.04633. And that gives us a concentration of 0.013296 moles per liter. Okay, now we go back to this Kb equation. So OH minus concentration is 10 to the negative 9.24 times 0.013296, all square rooted. What does this give us? 10 to the negative 9.24 times 0.013296 is 2.766 times 10 to the negative 6 moles per liter. And because to figure out pH we need the hydronium concentration, this is given by Kw divided by OH minus, and Kw is 10 to the negative 14. So 10 to the negative 14 divided by this 2.766 is 3.615 times 10 to the negative 9 moles per liter. So the pH, again, is just a negative log of that. So negative log of that is 8.44. So that's the pH at the equivalence point. But again, we have made an assumption, and it's that the it's very similar to the assumption we made before, and it's that this is equivalent to 6.16. Oh, sorry, equivalent to this 0.0133296. What actually happens is, because the ethanoate ions enter into equilibrium with water, as seen here, the concentration of ethanoate would actually decrease slightly, because it dissociates back into CH3COOH. And so the concentration of ethanoate is no longer 0.0133296. It's slightly less. But again, because it's quite a weak acid, and the conjugate base would also be, the equilibrium in that process would actually be not so favored in the right-hand side, the decrease in the concentration would not be significant. And so we can this assumption in the general case is fine. And so that is the other assumption we have made throughout this calculation. And then, of course, we have last part, which is after 35 mils of calcium hydroxide solution has been added. So in this case, the total volume, let's see, the total volume, let's separate this again. Total volume is equal to, we know, 35 mils plus the original 20 mils is 55.00 mils of calcium hydroxide. What's going on? And we know we can figure out the excess of calcium hydroxide that was used. So we know that at equivalence point, 35 mils was used. Oh, sorry, 26.33. Wrong number. At equivalence point, 26.33 mils was used. And of those 26.33 mils, all the hydroxide ions have been used to neutralize the ethanoic acid solution. But then we have the excess, 35.00. So basically, an extra, let's see, 35.26.33, an extra 8.67 mils of sodium of hydroxide ions are present, which didn't react with the ethanoic acid solution, because the ethanoic acid solution by this point has already been fully neutralized. So basically, we have the unreacted OH minus, or number of moles of OH minus, and that's equal to 0.00867, or the volume in liters, times its concentration. So let's see, where's the concentration? Where is the concentration? Oh, there we go. 0.2399 or 2339. So 0.02339. So what does this give us? 0.00867 times 0.02339. 2.0228 times 10 to the negative 4 moles. But this is the number of moles of hydroxide ions which didn't react. But we still have to figure out what the concentration of hydroxide ions is. And that is just simply the number of moles of hydroxide ions which didn't react, so it's still in the solution, divided by the total volume, which we figured out before is 55 mils. So it's 2.028 times 10 to the negative 4, divided by 0.05500, so 55 mils in liters. 0.055, so that is 3.687 times 10 to the negative 3 moles per liter. And then same thing applies here. We can figure out the number of the concentration of hydronium ions using Kw divided by hydroxide ion concentration. So it's 10 to the negative 14 divided by 3.687 times 10 to the negative 3. So that gives us 2.712 times 10 to the negative 12 moles per liter. And the pH here would therefore be the negative log of this, so 11.57. So we figured out the pH in all three of the cases. So initially it was 3.14. At equivalence point it was 8.44. And then after 35 mils of the calcium hydroxide has been added, it's 11.57. And we've also identified two assumptions we've made along the way. There is another assumption that we can make, that we did make throughout this calculation, and it's the fact that because water can dissociate to form hydronium ions and hydroxide ions, these ions can contribute to the pHs that we calculated before. And so this can mess up our calculations, and we didn't account for this in our calculations. However, the equilibrium constant for this equilibrium is 10 to the negative 14. And so the extent of the solution this way is actually very low. And so we can assume it to be negligible. So now moving on to part 3 of question 3a. Bromomethyl blue is a pH indicator which can be used in acid-base titrations. In solutions of low pH, the indicator is yellow in appearance. In solutions of high pH, the indicator is blue in appearance, or blue in color. During a weak acid, strong base titration, the solution is observed to transition through a green color as the pH rises. Discuss these observations with reference to how the composition and colors of pH indicators change during acid-base titrations, and comment whether this indicator would be appropriate for the titration between ethanoic acid and calcium hydroxide. No calculations are required. And they've given us the pKa for bromomethyl blue. So, there's two components to this question again. Observations of color changes and why that happens, and comment whether or not this would be appropriate for the titration that we have been calculating before. So, how pH indicators work, which is sort of what you need to explain for this question, is pH indicators are basically just acids. And we usually call them HIN, where IN is indicator. And they enter into equilibrium with water to form IN minus plus hydronium ions. So these indicator molecules are basically weak acids, and they form an equilibrium with water just like any other weak acid would. The protonated form, HIN, would be of one color, and the deprotonated form of the acid-base indicator, IN minus, would be another color. And so in this case, or in a general case, protonated forms are usually what happens in a low pH. So this would be low pH. Because in a low pH solution, the number or the concentration of hydronium ions is quite high. And if the concentration of hydronium ions are high, this equilibrium is shifted backwards. And so HIN would also be high. Which means HIN would be present in a low pH solution. And so in this case, in solutions of low pH, the indicator is yellow. So that means HIN is yellow. And the opposite is then true for IN minus. So IN minus is present most predominantly in a solution of high pH. And they tell us that the indicator is blue in color in solutions of high pH. So this is blue. And roughly in between, where it's like a medium sort of pH, where both HIN and IN minus are present in like roughly equal amounts, you would expect a mixture of the color, which is why you expect a green color as the pH rises. So that's how HIN and IN minus, indicator molecules, give these color changes. And so when you have an acid-base titration, you would be, in the case of ethanoic acid and calcium hydroxide, you would be continuously increasing the pH because you're continuously adding hydroxide ions. So if you're increasing the pH, the color will transition from yellow to green to blue. And so that's how the indicator would change color depending on the pH, which depends on how much base you've added to this titration. And now we have to comment on whether this indicator would be appropriate for the titration between ethanoic acid and calcium hydroxide. What's important to note here is the pKa. So the pKa is 7.2. And what does this mean? There is quite a nice explanation for what the pKa of 7.2 actually means. If we recall the Henderson-Hasselbalch equation, so pH equals pKa minus log base 10 of A minus divided by HA. Hopefully you're familiar with this equation. So if the pKa was equal to the pH, I believe that's a positive actually. If the pH was equal to the pKa, right, just for the sake of argument, these two would cancel. And so log base 10 of A minus divided by HA would equal 0. And then you can cancel out the log using log rules, and that would equal 1. So that means the concentration of the acid and its conjugate base are equal. And this is also the half equivalence point in any titration. So what does this mean in the case of bromomethyl blue? That means when the pH is equal to 7.2, the color of the solution would be green, because the conjugate base and the acid would be present in roughly equal amounts. And there's a general rule for how much how far away from the pH you can sort of deviate, and that is a plus or minus 1 rule. So if your pH lies between 6.2 and 8.2, then it's good enough for pH. If the pH lies between these two numbers and the pKa is like lying within those two numbers as well, then equivalence point pH, then the indicator is good enough to indicate whether or not the solution is good enough for the titration. But we know what the equivalence point pH is, and we figured it out in this question, and it was 8.44. 8.44 lies beyond this range. It's slightly beyond, and that simply means that bromothymol blue would not be appropriate for this titration. So bromothymol blue is not appropriate. So now we move on to part 2 of question 3b. Suggest reasons for the differences in formation enthalpy values for calcium oxide and carbon monoxide. So formation of calcium oxide would just be calcium plus half O2 gives us calcium oxide, and delta FH for this reaction is negative 635. And then the other formation is carbon plus half a mole of oxygen gives us carbon monoxide, and then delta FH would be negative 111. So we can consider this in sort of two different aspects. Calcium oxide releases more energy when it's being formed from its elements. And we consider this in two aspects. So delta H, we know delta H is given by sum of the delta H of all bonds broken minus sum of delta H bonds formed. So that means we consider whether or not if this is higher or lower, or whether this is higher or lower. So in the case of calcium and versus carbon, this is solid, because oxygen is the same. So that's the constant factor between the two. In the case of just reactants, in between the calcium and the carbon would actually have stronger bonds than the calcium, because the standard form of carbon is graphite, and graphite is a giant covalent network of carbons. Oh, wait. That looks something like this. It's like a hexagonal network. And these covalent bonds are very, very strong. And because of this, these bonds, as compared with Ca, which would be Ca2+, Ca2+, it's a giant metal lattice with electrons flowing between them. The bonds between these the metal ions and the electrons, or the metallic bonds, are actually weaker than the covalent bonds here. The covalent bonds are typically quite a lot stronger than any other sort of bond. And so bonds broken in the case of carbon monoxide would be higher. It's more endothermic. And so in this case, it's higher for carbon monoxide. And because it's higher, it's more endothermic, and that would contribute to delta H being more positive. And that's why this is more positive than for calcium oxide. And then we can also consider the other aspect, which is bonds formed. Not sure why that's not disappearing. Anyways, bonds formed in this case, we have calcium oxide, so it would be O and then Ca. So this is 2 minus, 2 minus, 2 plus, 2 plus. We have an ionic lattice here. And in the case of carbon monoxide, we simply have this, this, this. And they're molecules. They're individual molecules with delta negative, delta plus, delta negative. And we have these intermolecular bonds here. The thing is, these ionic bonds, because of the electrostatic attractions between the positive and negatively charged ions, they're so much stronger than the intermolecular bonds here between just the polar carbon monoxide molecules. And so the energy released by the formation of the carbon monoxide bonds would be less because the bonds are weaker. And so because it's less, and because of this negative sign here, the energy released from the bonds formed would contribute to a more endothermic formation enthalpy value, or a more positive formation enthalpy value, which is again why this is more positive than the number up here.